Hey everyone, we are going to review for your quiz on sections 1.2 and 1.3, finding limits from a graph, numerically, and also analytically. All right, if we take a look at the graph, we're going to find each limit value, and I just want to call your attention to two functional values, C and H. So just watch out for those two. Okay, so our first one, part A, asks us for the limit as x approaches -3 of f of x. So the graph itself is of our function f of x. We're going to take a look on the graph where x is equal to -3, and there's x equals -3. Mark it on the x-axis right here. And so we want to take a look at the two pieces of the graph to the left of -3 and to the right. So coming in from the left, we see that the y values are getting larger and approaching +7. And also the graph coming in from the right, the y values are approaching +7. So even though there's a hole exactly at +7, we'll still say that our limit as x approaches -3 of f of x is +7. Because remember, we're talking about the behavior of the graph close to, but not all exactly at, x equals -3. So as we're approaching x equals -3, y is getting closer to +7. All right, in a different portion of the graph, we're going to take a look at the limit as x approaches 0. So if you notice, and I'll use a different color in here, as we approach x equals 0, so there's where x is equal to 0. We want to come in from the left of that point. So I'm going to use green right in here. So coming in from the left of x equals 0, notice that y is approaching 1. And coming in from the right, notice that the y values are approaching -4. So in this particular case, we're going to say that the limit does not exist, because we're approaching two different y values. And I just want to remind you that you cannot say undefined for this, okay? So we don't say undefined when a limit does not exist. We have to say DNE, or does not exist. All right, I pointed out C earlier. It's a functional value. So what that's asking us to do is look at where x is equal to 8. That's this point over here. So I'll color it in blue. And it was a filled in circle. I didn't just fill it in with blue. It was already closed in. So when x is equal to 8, y is equal to 0. So just a functional value, not a limit in that case. All right, now we're going to find the limit as x approaches 8. So we're not going to look at that point. Instead, we're going to look at the graph down below here. As we get closer and closer to x equals 8 from the left, notice that the y value is -6. And as you come in from the right, the y values are also approaching -6. So we would say the limit as x approaches 8 is -6. Again, different than the functional value at x equals 8. All right, for E, we're finding the limit as x approaches -6. So we're over at this point on our graph, -6, right here. And we don't see any dots there, so we just want to trace with our finger. I'm going to use the highlighter tool again. We're going to come in from the left and get closer and closer to x equals -6. Come in from the right, and we're right there at this point from both the left and the right. So that limit would be equal to +1. Right, so from the left, as we get closer in here, y is approaching +1. As we come in from the right, y is also approaching +1. Okay, on to the next one. We want to find the limit as x approaches +4. All right, my eye is drawn to this place here at y, or at x equals 4, I see an asymptote. Okay, to the left of this asymptote, we are approaching positive infinity, and on the right-hand side of this asymptote, we are approaching negative infinity. So in this case, we have to say that the limit does not exist, and it's because we're approaching two different infinities. Okay, for g, we are finding the limit as x approaches -8. So notice that we've got another asymptote over here at x equals -8. And check it out, on the left-hand side, your graph is coming in really close to that asymptote approaching negative infinity. And also on the right-hand side, it's coming in close to that asymptote, also approaching negative infinity. Okay, so what I told you in class is that technically this should be does not exist. However, I also said because both sides of this graph are approaching negative infinity, I would accept that as an answer. Okay, be careful with question H. It says we want to find f of -3. So let's go back to this point, x equals -3 on the graph, okay? And look at that open circle right there. And look above and below and notice that there is not a filled in circle above or below. So we would say f of -3 is undefined. Okay, it's a functional value. It's undefined. You cannot say dne for this. Okay, so for functional value, it's either going to be a number, like if there's a filled in circle, you're going to give me that y value, or if it's an open circle, you say undefined. We never say it does not exist. All right, one last one, back to limits. We're finding the limit as x approaches +2. So find +2 on your graph. I'm going to try to pick something that stands out here. Here's +2. And I wrote that a little funny there, so let's clean it up. This is x equals +2, so we want to trace the graph coming in from the left, right here, coming in from the right, and notice that when x is equal to +2, we're taking a look at this point right here on the graph. So I'm just going to make it a little bit bigger, and that y value of that point is -2. And just keep in mind, a limit is a y value. Okay, a limit is a y value. So you're describing the behavior of a graph close to a point, but maybe not exactly at that point. All right, in the second group, I'm going to do just 2 problems right here, and then I'll move into more space for the ones that require more algebra. And the 2 that I'm going to do here are 2 problems that we can do by direct substitution. And that would be question A and question F. Okay, so question A, I know it's a rational function and there would be a domain restriction. X would not be able to be equal to -11, which isn't a problem because it says we're finding the limit as x approaches +11. So we're able to use direct substitution here. And by direct substitution, I mean plug it in. So I have 11 minus 11 over 11 plus 11. Okay, before you freak out on me, it's 11 minus 11 in the numerator. So that's 0 in the numerator divided by 22, which is just 0. That's your limit. Okay. It's okay to have 0 in the numerator, not okay to have 0 in the denominator. That's undefined. All right, the other one that we can do by direct substitution is f. There are no restrictions on the domain for this one because it's an odd root, okay? So no restrictions, no domain restrictions. So plug it in. So we'll see the cube root of 2 times 5 squared plus 14. All right, so we've got the cube root of 25 times 2, which is 50, plus 14. That's the cube root of 64, which is just 4. 4 to the third power would give us 64. All right, so on to another slide where I have more room to do the remaining problems. Okay, so number 2b, we have the limit as x approaches 7 of the cotangent of pi times x. So we're finding the limit here at the cotangent of 7 pi. So for trig functions, I would really encourage you to look at the graphs, and you'll have to make these on your own on the quiz. And the cotangent function actually has asymptotes at every pi, whole number pi. So at pi and at 2 pi and so on. So I'm going to draw on those asymptotes. So at 0 radians, pi radians, 2 pi radians, we have asymptotes. Okay, what happens in between is that the tangent function is going to cross the x-axis at pi over 2 and at 3 pi over 2. And the cotangent function falls to the right. In other words, it hugs this asymptote, comes in, crosses the x-axis at pi over 2, and then keeps going downward. It's going to keep following that pattern over and over again. So if you notice, at every multiple, whole number multiple of pi, we're approaching two different infinities. Negative infinity on the left, positive infinity on the right. So the same thing is going to be happening way out there at 7 pi. So we're going to say that this one is DNE because it will be approaching two different infinities. Okay, and number 2c, this is one of our favorites with the complex fraction. We're finding the limit as x approaches 1, and that does mean that we end up with division by 0, right? That is our domain restriction. All right, so we know right away, we did a quick check, x cannot equal positive 1, so we have to use one of our analytic methods for finding the limit. For this one, that means finding the least common denominator, or LCD, and that least common denominator is going to be 3 times x plus 2. We only care about the denominators of these two fractions. That's what's making it a complex fraction. So what we're going to do is multiply both the numerator by 3 times x plus 2 and the denominator by 3 plus x plus 2. So it's going to get a little big and messy. I'll write it all out so you all can see it, and then we'll simplify it. So keep your limit notation. Limit as x approaches 1, and we're going to take 1/3 times 3 times x plus 2, and if it helps, put it over 1. Okay. Watch out for this minus sign. Don't lose it in there. So we want minus. And then we want to take our fraction 1 over x plus 2 times our LCD, 3 times x plus 2 over 1. So I'm taking the LCD times both fractions. In that denominator, put it all over 3 times x minus 1 times x plus 2. So we're multiplying these together, but do not distribute. You can, but you're really just making more work for yourself. Okay, so now we want to simplify. So you're going to simplify here and simplify here. That's the fun part. Cross off I crossed off the wrong thing, of course. I'm going to cross off our factors that are going to reduce. Those 3's reduce. So what we're left with is the limit as x approaches 1 of x plus 2. And you can keep it in parentheses if you wish. Okay, minus. Over here, the x plus 2's are what divide, and we're left with a 3, so minus 3, all over this denominator, 3 times x minus 1 times x plus 2. Okay, keep the limit notation, so limit as x approaches 1, we have x plus 2 minus 3. You don't really need to take that step, but for those of you that need it, I'll put it in there. Okay, so that would give us the limit as x approaches 1 of x minus 1 now. All right, so it's no coincidence. All right, so what's going on here is we have an x minus 1 in the numerator and an x minus 1 in the denominator, right? That's what should happen every single time. Wherever your function was discontinuous, we're trying to remove that discontinuity. So if you've done your algebra correctly, that should divide out now, leaving you with a 1 in the numerator. So we have the limit as x approaches 1 of 1 over 3 times x plus 2. The issue with the denominator has been resolved, so plug in your 1. So it'll be 1 over 3 times 1 plus 2, or 1 over 3 times 3. 1/9 is our limit. All right, okay, let's keep going. Okay, in number 2D, we have an issue here because we're finding the limit as x approaches 0, and 0 would make this denominator equal to 0, making our function undefined. So we want to multiply by the conjugate. So the conjugate would be the square root of 7x plus 9 plus 3. We have to do this both in the numerator and the denominator to keep things equal. Okay, so we'll write the limit, keep that limit notation. In the numerator, when you multiply those conjugates together, the square root of 7x plus 9 times itself gives you 7x plus 9. The outside would give us positive 3 square root of 7x plus 9. The inside would give us negative 3 square root of 7x plus 9. And on the end, negative 3 times positive 3 is negative 9. So watch out for silly mistakes like on the sign, and also like doing something like adding 3 and 3 and getting 6 instead of multiplying. In that denominator, don't distribute, okay? You're going to hear me say that a lot with these analytic problems because you want to keep it in factored form because we're trying to get to a point where we can divide out an x from both the numerator and the denominator. So keep it factored. All right, here, those two are like terms, or they're opposites, so combine them together. And also here, positive 9 and negative 9 will add to 0. So as I mentioned, we're trying to get to a point where we can divide that discontinuity out. And notice we now have an x in the numerator and an x in the denominator. So we have a common factor. Okay, so this x and this x will divide. And now we're left with the limit as x approaches 0 of 7 over the square root of 7x plus 9 plus 3. And now you're ready for some direct substitution. Drop the limit notation and then plug in 0. So this would be 7 times 0 plus 9 plus 3. All that is going to do is give us the square root of 9, which is 3 plus 3. Our limit will be 7 over 6. And again, just keep it as an improper fraction. All right, and we've got a cosine function as part of our problem here. We're finding the limit as x approaches negative 3 of the cosine of pi times x over 4. Well, cosine graph is continuous, so you can find the limit anywhere. There are no breaks, there are no holes, no asymptotes. So jump right in to the cosine of negative 3 pi over 4. All right, so if you need to convert it to degrees, so it'll be negative 3 times 45 degrees, or negative 135 degrees. And that's going to put us into, because it's a negative angle, it's going to put us into quadrant 3. So reference angle is equal to 45 degrees, and as I mentioned, we're down here in quadrant 3. So for a 45-45 right triangle, the sides are 1 and 1, hypotenuse is the square root of 2, but in the third quadrant, they're both the x and the y are negative. So what we should know about cosine in quadrant 3 is that it's going to be negative, and cosine is adjacent over hypotenuse, so we'd have negative 1 over the square root of 2, and you need to rationalize that. So multiply numerator and denominator by the square root of 2, and we get negative square root of 2 over 2. Final answer. Okay, we already did 2f earlier. In case you missed it, that answer was 4 for that limit, but you can rewind it a little bit because it was a direct substitution problem. All right, so going on to 2g. First, take a look at that denominator, set it equal to 0, so you can figure out our domain restrictions. And 2x squared minus 5x minus 3 factors into 2x plus 1 and x minus 3. I knew that was going to happen. So two domain restrictions, x cannot be equal to negative 1/2 or positive 3, and that's the issue. If we plug 3 in there, we would actually end up with 0 over 0, which is indeterminate form. So that's a clue that we can do something to remove the discontinuity. And what we can do is factor and reduce. So in that numerator, I know I can factor out an x to start and get x squared minus 9, which happens to be the difference of two perfect squares. So we're going to factor that further. In the denominator, we already did that hard work of factoring, so rewrite it as 2x plus 1 times x minus 3. Okay, let's get that numerator factored completely now. I know I'm taking it like in stages. You can try to do more in one step, but I would encourage you to take it one baby step at a time. Okay, so x squared minus 9 factored really easily into x plus 3x minus 3. That denominator factored into 2x plus 1, x minus 3. And here you go, x minus 3 is divide out. We remove the discontinuity. We remove the issue of being able to plug in positive 3. So now we're left with the limit as x approaches 3 of x times x plus 3 over 2x plus 1. You're ready for some direct substitution. So now try plugging your 3 in. 3 times 3 plus 3 over 2 times 3 plus 1. That would be 3 times 6 over 6 plus 1. 18 over 7, and leave it as an improper fraction. All right, you guys, so I did a quick sketch for this one. We're finding the limit as x is approaching pi of the cosecant of 5x over 3. And when I plug in pi, it'll be the cosecant of 5 pi over 3. And I think we just need to do trig exact value. And I'll explain why really quick. So if we draw a quick graph of the sine function, which you can see here in blue, and I'm going to highlight it in light blue. All right, sine crosses the x-axis at 0 and at pi and 2 pi and 3 pi and 4 pi and 5 pi and 6 pi. Well, that's important to know because that means that when we draw the cosecant graph, we would have asymptotes at 0 and pi and 2 pi and 3 pi and 4 pi. All right, whole number multiples of pi. We don't have a whole number multiple of pi here, so that's how I know I want to do trig exact value. So if you can remember how to graph the sine function, then you should be able to graph the cosecant function, its inverse, by looking at the places where sine was equal to 0, and then going in and drawing the asymptotes for the cosecant function. Okay. All right, so now we know we're doing trig exact value. Our reference angle is pi over 3 or 60 degrees. So if you need to convert this to degrees, sorry, I almost wrote cosine, it's cosecant, cosecant of 300 degrees. All right, that's going to put us into the fourth quadrant with a reference angle of 60. So across from 30 would get the 1, across from 60 would get square root of 3. Hypotenuse would be 2. This square root of 3 has to be negative in quadrant 4. And so since we're doing cosecant of theta is equal to 1 over sine theta. And sine theta is equal to opposite over hypotenuse, or y over r. So we want to do r over y, or hypotenuse over opposite. So our hypotenuse is equal to 2. The opposite side would be negative square root of 3, because opposite the 60-degree angle, and then we have to rationalize. So multiply top and bottom by square root of 3 to get 2 square root of 3 over negative 3. And that negative can be out in front, or it can be in the numerator with the 2, like that. Either way, it's fine. All right, well, we don't have to worry about the last problem. I'll do it anyway. You won't have one like this on the quiz. Okay, so in number 2, part I, we're asked to find the limit as x approaches negative 1 of g of f of x. So we have to start by finding the limit on the inside function first. So we want to find the limit as x approaches negative 1 of f of x first. And then we're going to plug it into the outside. All right, so the limit as x approaches negative 1 of x squared plus 5x plus 4 all over x plus 1. Well, if I plug negative 1 in now, we'll run into trouble. We'll get 0 over 0. So what we want to do instead is factor and try to remove the discontinuity. And this factors into x plus 4, x plus 1. All over that x plus 1, the discontinuity is removed. So now we can plug in negative 1 for x and get negative 1 plus 4 is equal to 3. So now what we need to do is to find g of 3. So go to your function g of x, and we're ready to just go ahead and plug in the 3. So it'll be 13 minus 3 times 3 squared, or 13 minus 27, for a final answer of negative 14. And again, I did not put one of these on the quiz, so just focus on studying number 1, all the parts, and number 2, A through H. All right, as always, if you have any questions, get in touch with me.